Good afternoon, YouTubers. I have a special request. Somebody asked me to do a leaf and drag analysis on some solar panels that he's putting together. And basically, he sent me an idea, a kind of a croquis of how things will look like in a sketch. And within this sketch, I have back winds of about 140 miles per hour. These are hurricane winds, right? And through the back of the installation of the solar panel, and basically this wing will try to make the whole thing look more like an airplane wing with wings of this magnitude. Now for the design, he's gonna have about a length of 3200 mm on this side and about 1000 mm on this side. And for me, for the analysis on SolidWorks for CFD, computational fluid dynamic, I will only analyze 1, 2, 3, 4 up to 4 only. This side here, 1/3 of the total. Just to my machine is not that fast, so trying to analyze the whole thing and getting the accuracy that I would like to have will require small grid, and that will create problem. And the system might not be good enough. I have an i5 machine. It would be greater if I have an i7 or something superior than that, but with an i5 16 gigabyte, I think that I will be able to make this analysis of about 8 solar panels within the reasonable time. We'll see. Now, more of this design. Let's see. This is basically a side view of what it have. Basically, the 3200 come from 2 of these solar panels together for a total of the 3200 mm. Now, the angle is very important. The angle will be at 25 degrees. So the wind coming through this side, which are the worst. So that's what the one that you want to definitely design for, to ensure that this solar panel is anchored properly. The distance from the bottom of the solar panel is about 255, and the top one here is about 1647. You have to check your local code to see whether this meets this spec meet your local code. Very be sure. Sometimes they don't want your high side be too high or your low side be too low. So you have to be within your local spec, so always check that. And now what I will do is basically just concentrate on the solar panel. I will not, since I'm not trying to do a stress analysis on the frame, I will focus basically on the solar panel only. And so for leaf and drag, more like an airplane design, or this is come from some pages from NASA website. Coefficient of lift basically is a lift force divided by the density, the wind speed square, the area of that solar panel, and divided by 2. So for drag is the same. The coefficient of drag will be the drag force, and if we want to talk about coordinate, will be on this will be on the X side, and this will be on the Y side going up, and this is going in the direction of the wind. And the area of one side of the solar panel is 3.2. Since we are working with 4, that's a total area of 12.88 meters square. Wind speed about 140 converted to m per second, so that's going to be 62.59 meters per second. So that's the number that you punch here. After you get the L or the D, depending on the case. The air density, we are talking about 25 degrees. This doesn't change much. I mean, you can take a look here. 25 degrees, between 30 and 20. That's where you mostly will be in most cases. So now, one little thing that you want to be, concerned with is that I can definitely put like a solar, like a plate at an angle, but I want to do a little bit more than that. And there's a frame within the solar panel that will catch more air, so you want to be sure that you kind of include this into your design somehow. And that's a good point, just to to ensure that you definitely are close to what it is. You can do, sort of like put together a frame or something and see what happened. But definitely I will try to include this part here, all this, which creates sort of like a boundary within your solar panel, catching more air and trap it, sort of that the air get trapped within. That might create more drag issue. Now the other thing that you want to be also concerned with is with the floor. So you want to put a floor into your design on SolidWorks, because the idea is that this will create some ground effect, and so include that as well. Well, with that, all that information said, let's get busy. Let's get to work and let's see what happens. Let me close these so this get to somewhere here so I can still see it while I'm designing very quickly. So I put right. That will do. Now let's start busy here, and let's do quickly a center line. Actually, let me put that line anywhere. Let me get it. Actually, I like to put that lines anywhere here. That will do. Now let's change the unit, and let's go back. So let's say that this line and this point here, all right, that will stay there. Now let's put together that one got messed up. There we go. Those two lines should be equal as well. Now let's see. There we go. Now let's reduce this a little bit, and let's get busy. Let's put a line here, a center line somewhere. That would do. This is for the floor, so I want to be sure that the distance between that line and this line stay at 255. So now you start to see the dimension of where I'm going, and so let's see what else. Now let's increase this part here so I have a good idea what I'm doing. And so let's put this dimension here. Since this is gonna be this that's the long side, that's 30, that's this side here time 2, that's 3200. So we write the 3200 mm, and let's make this smaller so I know what I'm doing. And let's move. Let me pop this big because it's gonna be hard to centralize what I want. So let's see. Now I have to open this a little. Well, actually, for that, let me expand this guy. That's for the floor, and there's a distance here, right here above here, that I want to be sure that I have to be. Let's see if I can see that point versus this point here. That distance has to be 1647. Good. So now I got the whole thing pretty much the way I want it. So let's see. It's still under defined, meaning that I probably have to put another dimension or put another constraint here. Let's see what that would be. So I got that one. This is black, this is black, this is still blue. Maybe if I specify this, actually let me see something here. Let me see what this line is doing. Sorry, escape. There we go. 4372. That's right. Yep. If I specify that, then the whole thing is done. So I got everything set. So now everything is well specified. I got the dimension. Let's close this a little bit. So we let's see if I can move it. Let's see. There we go. Okay. 255, 1647 at the top, and 25 degrees. Everything's set. Escape. Let's check a little bit more. Actually, yeah, more detail here. Yep, everything's set properly. I guess we are ready to go. Now, I don't have the floor. Actually, well, I know where it's gonna be. What we're gonna do now, if anything, is extrude this. And for the extrusion, that will be, you remember this, it's gonna be 4 times this dimension, 1006, and to get here to 1/3 of the whole solar panel. So let's do that. Let's extrude mid plane. That will be 1006 times 4. And that will do. Let's see how this looks like now. Let's accept that, and we are right. Rotate view. Yep. So we got the. This will be more than enough, but there's a couple things that I need to be sure that I have. One of them is the floor, and also that I kind of do sort of like a shoebox lid type of to catch more air. So, all right, so we have the completed extrusion. So now let's do a hole here somehow. Let's see, we can use shell perhaps. Let's identify that face, and let's see, let's do should be 3 millimeters. Let's see. It's a thinner wall. That would do. Now I have more air to catch inside, but that would do. That's a quick way to do it. Let's rotate this, and so definitely look more like a shoebox, and that will do, which is basically what we have. Let's rotate this again. Let's see. And so what I'm planning to do is see if I can put if you go back here for a second, this part here, since I already have this part on the whole thing, you know. Don't use this dimension. I'm going through what I have here. Basically, that's the dimension I'm using. And going back here, and then again, what I need to do is go, let's see if I can go here. And this is the part that's going to be interesting. Let's see if I can do that. The lead, and then cut that just to make what I want to make. So I want basically that border. I want to construct over that border, and to do that, now I need to increase a lot just to see what I'm doing, because basically the idea will be to do line in a general sense. There we go. And now let's make the box, and then we go and do a couple of things. Let's see. And now let's go here and do the following. This line and this top line, they need to be collinear, and this line and the line outside need to be collinear as well. Oops, did I miss something here? This line and this line need to be collinear. So now let's do a check, and let's open this size, and this line and the outside line need to be collinear, and so the bottom and this line outside, they should be collinear as well. I think that we got everybody the way it should be. And now what we should do, feature, do an extraction. Let's rotate this a little bit so I know what I'm doing. Yep. Let's do a 3 millimeter extrusion. Now everything's sealed. Back again, rotate. Let's see, everything should be sealed. Yep, everything is sealed, but it's hollow. The internal is hollow. So what we need to do is now go back here. Opa, that's not it. Rotate a little bit, go back here again, and do let's see, I need to do, that would be an inch, so I have to somehow go do sketch and do line. Let's see. There we go. Now do the same trick like last time. Check what the border you're talking about, because basically the idea will be that we're gonna have about an inch from each border, from each edge. So let's see where we are, and let's increase this, and let's increase this. And here's the story. Let's go here and let's do from this to here. That should be 25.4. From here to here, that should be 25.4. And let's do the same on this side, which is basically from here to the outside. That should be 25.4, about an inch. And let's do the same right here as well. So that from there will be from here to here. That would be 25.4. I think that we got everything that we want. Let's reduce this to size, and what I should do now is cut that inside. Features, cut, and let's rotate this so we know what we're doing. Yep, it's looking good. Let's put this in the right direction. So that's X, and with the Y, it's going in the right direction. Yep. So now let's cut about 5 or 10. It doesn't matter. Well, it does matter. You don't have to cut too much that you cut to the other side. So you cut up to it said mid plane. Cut 6 maybe. Let's see. I think that if we roll now, we should be able to see the sort of the shoebox, but now we have an edge, an internal edge, which is what we were looking for. All right, let's see. Let's accept this and let's see how this looks like eventually. Rotate it back again. Yep. And everything looks more like a solar panel with that internal edge. Let's see, zoom to area, rotate. So yep, you can see all that internal area, and this all around is 1 inch going into it. It's only one, basically one piece. Let's see, rotate again. Actually, everything looks good. I think that we are ready to rumble here. Rotate view. That's basically it. Now let's do some markup, and just to ensure that everything looks good, some markups, and oops, measure the area. It's 12.88 meters square. That's good, and looks good. So everything else was well set. So now we have a sort of like a solar panel where air will be catch deep within the solar panel, and no floor yet. We don't have no floor. Let's see how it behave without floor, and then we do one with floor. So let's close this, and we are ready to go. So let's save this. Let's save the whole thing, and save. And now go to flow simulation, and let's hit the wizard, and next. Now velocity, let's change the unit here to miles hour, so make life easier. It's going to be external. Next, air, terminal turbulent. That's okay. Let's see where we are now. Wind in the x direction, going down. Okay, that's a positive x, meaning that I have to put here the number as 140 miles an hour, and finish, I guess. There's nothing more to it. Good. Now let's reduce this so I know the computational. Now this distance here is important. That distance is basically, I can use the core, so I will make that distance in the y direction at least in the x direction, in the x direction, longer from here. So that's going to be on the negative side. I will be about 3 times this distance with the core. If I had 3.2 times 3, so 10 will do fine on that distance. What's the idea is that I have, let's see, that's the negative one. Let's see, let's move that one. Yeah. So the idea is that I have on the stern wing very in the front of the solar panel. I don't want to start too close to it, so -10, that will be okay. In the outside, it's okay. It looks, I can make it smaller if I want to, but yeah, about 5. So it's going to be 10 and 5. Now, how about in this direction? Maybe 1 core will be okay. So 3 meters. How about in the negative direction? I can certainly use another 3 meters, -3. And in the C direction, I really don't care much about it. Oops, I put the wrong number. Yeah, sorry for that. 3 meters. There we go. And so if I rotate these, let's see how this looks like. See, this direction I definitely can How about this one? 4 and 4. I can make it smaller. Actually, let's see. 3 and -3. 3 and -3. Now let's rotate again. Let's see how this looks like. The only direction that I really care a lot is about the front of the solar panel, because I want very undisturbed air here, then start to hit this. Whatever happen will happen. So that's the idea. I have a big box. That's bad, just to say the least, on my i5 computer. So I have to be careful now with the mesh. I will reduce it at a later time, make it smaller and see what happens. But in the meantime, it's just a trial. Okay. It is a big box. So let's say okay. And now boundary conditions and boundary conditions. Let's see. Input data. Component control is only one, which is everything. There's nothing more into it. Now let's return back. And what is gonna be? I'm gonna leave the goals as a surface goal for the time being, and let's see. It's gonna be surface goal. For surface goal, I'm gonna pick these, obviously, and these the two most important faces. And now let's pick as well the side faces. That will be that one. Rotate a little bit. You're going to pick the internal faces as well of the box. So on the side you have a lot of surface to deal with. Internal and externals for faces. Let's see that one. Rotate view. Okay. I think that did I have all of them? Let's see. I think that we have everything. Yep. Yep, everything has been picked. That's the hard part. Sometimes you I don't see much of a big deal here. Everything looks good. I think that's one missing, or I have one more that I shouldn't. It's kind of weird. Why is tab 11? let's see, all our faces. Phase 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, let's see, let's increase this side here just in case I'm missing one. Nope, everything looks good. Oh, I see. Maybe it's just because of the board that I also include. Yeah. All right. So now let's do normal forces. So that will be this one, and this one. I include the three of them just for the sake of the argument. And let's say okay. And now let's do mesh, but for the global mesh, let's see. Let's start with a 3. Let's start with a 4. And let's reduce this, and let's move it somewhere here, and let's do manual, and let's show what it looks like. It's huge, very big dimension for the mesh, but it's to start with, you know. I don't want to bug the machine, so look good. Let's accept that, and let's create the mesh. That should be quick. Good. So we are ready to roll, and I have the forces, and I have the domain, and I have the mesh. So we are ready to roll. Let's run, and let's see how quickly we get this going. It's in the order of minute, not bad, but still, just because that mesh, that computational domain was big, it's gonna take a few minutes here and there to get it done. So this is the part that you walk away and let it go. Now it would be good to find out how our forces looks like. Put the three of them, and let's see to what point they are looking at. So drag force 1200 Newton. The force in the lift force about 26,000 Newton. And the force in the Z, obviously that's not a big deal there, but this looks, I would say, these kind of decent numbers, and not bad. 26, and there's no floor. Might be a little bit larger when I put a floor, but so far they look, I would say they don't look bad. Makes sense based on I didn't include the equation for lift and drag, but those lift and drag should be very close to, I don't know, 0.7 for lift and 0.4 for drag. And yeah, that was quick. This is 1/3 of the total solar panel design that he asked me to analyze. So this is 1/3. So these forces basically are 1/3 of the total. They are in Newton, so it's about to finish, and it looks very, very promising. Remember to be as far as 3 times or even more from the, I'm using the core for this analysis, just to ensure that when I go back now to do the plot of the pressure, I'm far away from, you know, where the action will happen, so the calculation will be better, you know, less errors and more accurate, for perhaps. This number might improve a little bit more if I use a better definition. I use 4, maybe I need to use 5 or 6. 7, it's just gonna take a while to get a 7 here, and looks like it's done. Now let's take a look to here, and this is what I'm talking about, flow trajectory. Let's insert one here, and actually, can I pick all of them? Nope. Oh yes, but it pick edges. That's bad. I want to pick faces. Rotate again. Maybe let's see if I can do edges and pull that one there. We'll see. Edges and 20. Let's start with a 20, and lines and arrows, pressure. Make it thinner, maybe 0.02. 20. Let's hit 40. Let's see. And this will be pressure. And let's rotate this. Rotate view. Okay. Yeah. See, that's what I'm talking about. Very undisturbed condition. As you approach, then they start to change. Rotate view. I need to add more lines definitely, but you can start to see the underneath pressure is somewhere here, and the pressure at the top of the panel it's more here, so definitely it's a push for the panel to go back and up, and those are the surface forces that we measure. Rotate view it again. Let's see if I can get this better. More lines might be better. Edit. I put, how many I put? 40, maybe a 100. I'll take a little bit while. I hope I don't bug the machine. Getting better. Again, that's pressure. Rotate. No bad. Now I can see a vortex, heavy vortex, the corners. I wish I have a better mouse, but anyway, that's what I have. Well, look good. That was if I plot, if I go here and do insert and do all, show, and here are the forces. 12,000 Newton on the drag and about 26,000 on the lift, and that's no floor. I would say that's kind of a low resolution. Maybe what I should do is add the two equations now, the lift and drag a coefficient, just to see whether they are within, you know, the expectation of computational fluid dynamics for airplane wing theory. And let's do that. Let's go back here. Let's get out of here, and let's remove these high, and let's do what I will do now is add again goals, insert equation goal, and let's do very quickly here. What should I do? What I will do is let's call this drag equation, gonna be drag coefficient, and for that drag coefficient will be the force in the x, and that has to be divided by the density of air. Let's put a parenthesis here. That was 1.184, and that had to be multiplied by the wind speed, and that wind speed was 62. Oops. 62.59, and that has to be square, and that has to be multiplied by the area, 12.88, and that has to be divided by 2, and close the parenthesis. So that's drag coefficient. I need, from this drag coefficient, I can pull everything here, copy, and this doesn't have unit, so put like no unit, and accept that. And now let's do one more. Insert a global equation, and for this one let's pick the force in the y direction, and let's divide that by, since I have to divide by here, sorry for that. Everything else look good. 62.59. okay, everything look good. This is lift. Let's get this is lift. That will do, and let's accept that. So I got everything now. Drag and lift, and the forces normal to the surface. It's important that you use normal forces, because when I add a floor here, this is going to be messy to understand what's happening. Now with that said, I guess that we are ready to rumble here again. Let's do a mesh again, but instead of 4, let's move to 1 notch, and let's show again. You see, this is getting smaller, and everything else stay the same. If I increase, let's say, to here, you can see that it's getting smaller. When I get to 7, now it's really small, and but that would take for a while. Let's go back to 5, and let's apply OK, and let's run that global mesh again. Good. So as you can see, it unload everything, because we're gonna run again. We're gonna run, and let's see what happens. Now what I will do is, as you can see, it already remember that I want to plot this, but I want to add another plot, which is for drag and leave, and let's say OK. And as you can see, drag about 0.5 right now, and leave about 1. So we'll see. They should drop. They are high at this point. They should be start to drop to a kind of a more general term, or general values of leaf and drag for at 25 degrees. Remember, this is not an airplane wing, but it looks like it, and that's why I'm analyzing it, to see what drag and leaf will do to this kind of a solar panel that has also this catching borders or frame for the air. And keep doing. Leaf is on the high side. Drag is getting more into what it's supposed to, about 0.4, my expectation. Leaf is still too high. We'll see if it gets to a more, I would say, I don't know, about 0.7 on the lift, but still high. Calculation is still going. So let's see. Wow, there's an expectation that this take about 11 minutes to get it done. Wow, that take a while. Yep, it's dropping. 0.9, 0.43. This is right where it should be. Drag, making a lot of sense. And but leaf still way high. We'll see. Now how the forces. Let's see. The forces should get close to what we get in the first time. Let's see what. Here we go. It was about 26. You remember? 26, and it was about 12,000, 26,000 on this one, and 12,000. This with a very low resolution. I think it was for the mesh, for setting the mesh. Start to get pretty much close now. It's closing. Probably maybe it will repeat itself basically with the same number, even with have a higher resolution. It look good. 27. Actually, if I got that from here. That's the original. See, 26,000, almost 27, and the 12,000. Yeah. So it's getting there, you know, as the first trial with a very low resolution. You know, I think that was 4. Going back to what I'm doing now, which is this one. Getting there. Then it's not changing much. Yeah, this is about to finish. Yep. Getting a little bit higher value, but not much. And so this one. So that's because I increased the resolution. That's when you want as accurate as possible, be as far away from the body that you are analyzing, but then you pay for the mesh. You pay on time. I mean, you have a slow machine, that would take for a while to get the results the way you want it. Now, going back to leaf and drag, let's see where they are. I think it was this one. Still calculating. I still believe that this leaf is a little bit on the high side. Still moving on it. Again, no floor. I'm wondering what happened when you put the floor. That ground effect will create perhaps more forces. It achieves it gets some value here, but it's still cranking. We want to wait because actually this has not, since the simulation has not been completed. That's what it said here, not loaded. You have to finish this. Let's see where we are now here. About 5 minutes.
2,000 years later.
It's about to finish. Yep, they're done. Excellent. So now we got everything. I can repeat this and let's get more accurate results. And let's see, based on the numbers that we have now, better resolution. So yes, you can see the pressure somewhere here, and now you see a lot of vortex. Rotate so you can see the back of it, and you can see what is happening at the bottom of the solar panel and the effect of these borders. Let's see if I can take a look to those. You see, the air hit those borders and they will increase drag and everything. And so those are the kind of nice thing that you can study with this simulation. Having those borders, look at this to see what the air needs to do. It's weird. and that create a lot of problem, and more drag and perhaps more lift, and that's maybe why I'm seeing a little bit more lift than what I was expecting. We can do actually, well, let's do here a play so that you can see what actually the air is doing. And start, so it repeat itself. And that's basically it. One more, let's do one more at and with this I call it quit for no floor simulation. Let's stop this, let's hide this, and let's go back to mesh, global mesh, and now let's hit S7, and this will take a while, so let's hit S7. And what else should I do? Go manual here for 1 second. As you can see on the 141 show, and let's increase this to 200 and take a look what happened when you see that 200. See, you are increasing this length here. The other one, like for example, you increase this to 300. Check what happened. You see, this gets smaller and smaller, and you get a lot more precision on what you're doing. But this will take forever, maybe days to get it done. Maybe. For the sake of the argument, let's go back here for a second. Let's go back manual. Actually, let's no automatic. Let's adjust this manual, and you see how smaller they are. But when you go automatic and adjust it to 7 and go manual, so now in 141, and number of cells on the X side, see, and this is the number of cells in the Y, that one, and number of cells in the C. So I would say here is the big deal in when I want to increase that to 200, and let's say this is okay. And now let's run that mesh again as a big mesh, and all this data is being kept within the computer. So what I need to worry is just to see increase to almost to 1 million number of boxes. So this will take a while to get it done. Now we are ready to run, and let's how much accuracy I can gain by running a fine mesh. Run, and let's wait here for a few 1 or 2 runs, because this is gonna be very it would take for a while. Now let's see, CPU time. I don't have any number yet there, and preparing for calculation. That used to be done very fast, but I guess since we are using a very fine mesh, we haven't seen any calculation yet, because still cranking. Well, I guess that now it start to crank. Let's see what is. Nope, I haven't posted any number yet where things will go. Oh, there we go. Calculation time left. No update yet on this. Wow, here we go. Well, at this first update might take 1 hour 17 minutes. So what we will do is basically bail out from here, and have a lunch, do something else, and come back, and hopefully let's see if I wait for another. This is 3 iteration already, 4. Let's see if the number is getting better or getting worse. 1 hour 29. still the 1 hour is there, so meaning that it's cranking a lot of numbers. You can see that the leaf is coming, it's kind of up and down yet, and so the drag, they are not in what used to be, but it's too early to call. So that's why you have to kind of validate this number, test them to see whether you have enough accuracy as you go along. And now let's look at the forces now. I think it's this one, 16 and 32. This is about 5,000 Newton above, and this is about 4,000 Newton above. They're both above of early studies, so it should drop. They should be dropping, getting close to what's supposed to be. On the C coordinate, pretty much nothing happening as expected. So let's see, this is still high, 1.11. If these numbers start to change, way too high, maybe that will prompt me to add more, to include kind of a fine mesh, to increase the mesh size, perhaps in the y direction as well. All right, just to to have a better results. But they are ballpark. They are still holding. Let's go back to plot 1. Yeah, still it's dropping from 27, about 27 versus 32 that I have here, still dropping. And so this one was 17, now it's in 15. It's getting close to the value with a kind of a larger mesh size. It's pretty much the way it looks like. Yeah, those numbers will repeat themselves back again, but they're going to take a while. I mean, as you can see here, this is just starting. It's going to take a while. So this is what I will do. I will be back in an hour, and let's see where we are. All right, and that will do. Maybe, yeah, or maybe return in another day. The result will be there waiting for me, and we will pick it from there. As I always said, have a great afternoon. Oh well, this finished. So here are the numbers for this last run. No floor, and it kind of increased a little bit, about 14,000, almost 30,000 here on the leaf force. Let's see. Yep, you can see that the leaf coefficient increased to almost to 1, and so the drag coefficient to 0.5 as I improve the mesh. So I will leave this like that, because these are kind of I would say kind of a refined results, given the fact that I definitely increased the number of I increased the mesh, and in fact I went over based on the mesh that I use on this one, and so I will leave it like that. Let's see how now the flow trajectory looks like. Let's show that one based on the new study, if we see any improvement. As you can say, take a little bit while, more point, and so forth. Let's rotate this a little bit. I can certainly do a few things here and there. You can see that most of it is on the non-disturbed zone, so I can reduce these a little bit. Let's say I'm using three times the core size basically for this length here, so I can definitely reduce to at least, I don't know, easily 2 without any problem. I can see no disturbance on this zone. Make that mesh smaller. Let's see. You can see the vortex right there as it comes from the back of the solar panel. It looks good. One thing that I might do, rotate again, is to definitely reduce this. Leave the same mesh size on the X direction, but just reduce it. Now that I'm certainly sure that the impact on this area it shouldn't be a problem if I reduce that, and that would make a lot of sense. That would improve the accuracy of where I want to have more points. What I mean, again, this is the kind of things that you have to do just to validate your results, just to identify where the area where you don't want to be. Like, for example, on this zone, you don't want to start here. That would be bad. So you want to be a little bit, before where the pressure start to rise. So you want to be somewhere here. So I definitely can cut this boundary and do one more run and see what happened. And the question is, do I want the full mesh size that I used last time, which take more than an hour to do so? I can gain a little bit more insight into that, but I'd rather at this point finish this where it is. Maybe let's see. Let's do perhaps. Let's show this where we are, and let's put all of them. So, and here are all of them the way they are. So I will consider these basically as the final numbers with that resolution. And X is about 15,000 newtons, about 30,000 newtons on the Y direction, and the average value, I will use average value, and the lift and drag coefficient, lift about 1 and drag about 0.5. And probably this number is a little bit higher than what they typically are because of this form, this kind of a catching air shoebox lid that the solar panel has around the frame, so they tend to be higher. It's like a parachute. It's actually like it looks like a parachute. They trap air inside, hard for the air to escape, and therefore it creates more lift and drag than a regular, let's say, a flat plate. On that line. Again, I'm kind of documenting what I did, so if somebody want to do this work again, they have a good idea of what was happening. And with that, as I always said, be safe, whatever be your final destination. If you want, again, this number need to be changed to pounds. If you want to change pound, just divide by 9.81, multiply by 2.2, and they will be in pound force, which more for USA units. Thank you. Have a great day.